smart material is a type of material that has the ability to change its own properties in response to stimuli. For example, changes in color, viscosity, or tensile strength. Mechanoresponsive smart materials are a specific class of smart materials which respond exclusively to mechanical stimuli, for example, tensile or compressive forces. The molecule oxazine has the possibility for various tunable, mechanoresponsive, and mechanochromic properties. Mechanochromic meaning that it changes color when it is mechanically activated. In order to simulate the molecule, the DFT, or density functional theory, and B3LYP computational models were used along with COGEF to simulate the reaction of the molecule to mechanical forces by setting a distance constraint between two atoms and gradually increasing that distance stepwise until a bond on the molecule would break. These simulations were run on the applications Spartan 2018 and Materials Studio 2020, with Spartan being used for the brunt of the simulation and Materials Studio being used to provide supplementary simulation data when Spartan produced unreliable results. In order to determine the forms of oxazine that exhibit the most ideal mechanoresponsive properties, 3 different forms with different polymer attachment points were created that all transfer the mechanical energy across the molecule in slightly different ways, leading to slightly different hypothesized properties, as the energy is transferred to the desired bond in different ways. For the different stretching modes tested on the OX1 molecule, 3 of the 9 modes produced the desired bond cleavage, with 2/3 of the successful stretching modes having the desired energy curves, while only 1/6 of the unsuccessful stretching modes had the desired energy curve. For the dihedral angle of the desired bond, the graphs of the successful stretching modes were characterized by a sharp increase at the cleavage point followed by a steep decline, and the bond order of the bond in successful modes decreased slightly faster than the unsuccessful modes before dropping to 0 at the cleavage point. The OX1 and OX3 derivatives were determined to be the most viable forms of oxazine for mechanoresponsive properties due to their relatively lower amount of displacement needed for cleavage. The plot of the equilibrium dihedral angle versus equilibrium constraint distance reveals 2 distinct regions for successful and unsuccessful stretching modes. However, before any serious conclusions are to be drawn, the very limited data set used would have to be expanded.